All right, let's talk about acids and bases, and we're going to start where you would normally start, right? Let's start with some definitions, okay? Okay, now there are two different definitions of acids and bases that we use in this class. The older one, which is a little bit simpler, probably what you were introduced to in high school. Comes from the Swedish chemist Svante Arrhenius. And so this is the Arrhenius definition. And in the Arrhenius model, okay. So in the Arrhenius model, an acid is any species that dissolves in water to release H plus ions. And so a typical example would be something like hydrogen bromide. Hydrogen bromide is a gas, but when you dissolve it in water, it breaks apart. To give you hydrogen ions and bromide ions. Another good example is nitric acid, HNO3. And when you put that in water, it dissolves to give you hydrogen ions and nitrate ions. Since both of those release H plus ions, those are considered acids in the Arrhenius model. Okay. All right. A lot of the words here are the same, so I'm we'll leave the same thing up here. A base in the Arrhenius model is any species that dissolves in water to release, instead of H plus ions, hydroxide ions. And notice the hydroxides are anions, right? So for example, sodium hydroxide is a solid, and when you dissolve that in water, of course, you get sodium ions and hydroxide ions. You can also have things like calcium hydroxide, which has two hydroxides in it. And so when you dissolve this in water, you get calcium ions and two hydroxide ions. Okay. So in both cases, those are considered bases in the Arrhenius model because when you dissolve them, they release hydroxide ions. And in the Arrhenius model, we can talk about a neutralization reaction. And a neutralization reaction in the Arrhenius model is a reaction between an acid and a base, which produces a salt and water. And salt, in this case, just means a soluble ionic compound. It doesn't necessarily have to be NaCl. It can be, but it doesn't have to be. So, for example, hydrobromic acid with sodium hydroxide, for example. If you remember back to the chapter with solubility rules and net ionic equations, this is a double displacement reaction, so you switch the partners. And this will give you sodium bromide and water, right? And sodium bromide in this case is the salt. You can have, let's try this one. You can have sulfuric acid, for example. Plus KOH, this potassium hydroxide, and this would give you potassium sulfate, which is the salt in this case, and 2 water molecules. See that when you balance that out, you're going to get a 2 there. Okay. All right. So that about does it for the Arrhenius model. Like I said, that's probably what you were introduced to in high school. If you had AP chemistry in high school, then you may have also seen the second definition. This definition is a little bit broader than the Arrhenius definition, and it tends to work a little bit better for many cases. It explains things a little bit more completely. And this is the Bronsted-Lowry theory. In the Bronsted-Lowry theory, an acid is an H plus donor. It means it gives an H plus. And I should mention this terminology here. A hydrogen ion, or let's say a hydrogen atom has only one thing in the nucleus, and that's a proton. And it also has an electron around it, right? So when you take the electron away from a hydrogen atom to make a hydrogen ion, all you're left with is that nucleus, and the nucleus has no neutrons in it. All it has is one proton. So we often use the term proton in acid-base chemistry, and we're not talking about nuclear chemistry or anything like that. Proton is just another way of saying hydrogen ion, and it rolls off the tongue a little bit better, and so people typically talk about proton donors instead of hydrogen ion donors. And a base is a proton acceptor. Okay. And we'll see how that works. When we talked about the Arrhenius theory, you could describe an acid all by itself, because you put the acid in water, it breaks apart to give hydrogen ions. You can describe a base all by itself, you put it in water, it breaks apart to give hydroxide ions, right? So you don't really need an interaction between an acid and a base to define an acid and a base in the Arrhenius model. In the Bronsted model, you can only define an acid in the presence of a base, and you can only define a base in the presence of an acid. Right? So you have to have a reaction in order to describe this. Let's take an example here. If we take nitric acid and react it with ammonia, right, what we're going to get is ammonium nitrate. But because ammonium nitrate is soluble, it'll break apart into its two different ions, right? Now, if you look at this, you can see what's actually happening is this hydrogen is coming off of the, separating from this NO3. This whole thing together is nitric acid. The hydrogen comes off, and the hydrogen binds to the ammonia to turn the ammonia into NH4. Right? So that means that this nitric acid is giving up one of its protons, giving up one of its hydrogen ions. So this would be a hydrogen donor, and that would be a hydrogen ion acceptor, right? So this would be the acid, and this would be the base. All right. Let me make a brief parenthetical statement. Let me digress a little bit. Okay. Hydrogen ions in water, because hydrogen ions have such a large charge density, they attract water molecules and stick to them. Right? So if you have a hydrogen ion in water, it's going to grab one of those water molecules, and in fact it usually grabs more than one, so you can get a cluster of water molecules around this H+. So hydrogen ions don't actually exist in water all by themselves. Hydrogen ions in water usually actually exist in this form, or as I said before, with even more water molecules coupled onto them. Nevertheless, we will very often write hydrogen ions this way. Okay? Depending on the reaction, depending on what's going on, sometimes it's more convenient to write them like this. Okay? But I want you to know, in general, writing H+ or writing H3O+ is essentially designating the same species. Just the context might make this a little bit simpler, or it might make this a little bit simpler. All right. So we'll see both of those. All right. Okay. Now, the reason I mention that is because for Bronsted acids and Bronsted bases, the acid being the proton donor and the base being the proton acceptor, whether something is an acid or a base can actually depend on the circumstances. And you don't see this in the Arrhenius definition, but in the Bronsted definition, something is an acid if it acts as a proton donor in that particular circumstance, and it's a base if it acts as a proton acceptor in that particular circumstance. So it can differ from one situation to the next. for example, and this is one of those circumstances where it's helpful. You'll see what we're going to do with the H2O. All right. Hydrochloric acid is a strong acid, and so it's going to lose its H plus to its H plus over here, but because there's water around, that H plus is going to bind to that water molecule. So in this case, what's happening is the hydrochloric acid is donating its proton to the water molecule to make H3O plus. So this is acting as a proton donor, that's the acid. This is acting as our proton acceptor, and that's the base. On the other hand, we can have a situation like this. If water is put in a solution with, or let's say if ammonia is placed into water, we get a solution of ammonia in water, then a hydrogen will be transferred from the water molecule to the ammonia to make ammonium ions and hydroxide ions. And so in this case, the water is acting as a proton donor. It's giving a proton to the ammonia. So in this case, water is acting as a Bronsted-Lewis acid, and the ammonia is acting as a Bronsted-Lewis base. Okay. So we have some species like this that can act as acids in some circumstances and bases in other circumstances. And when you have a species like that, we say that such a species is amphoteric, which means it can act as an acid in some chemical reactions and can act as a base in other reactions.